I want to set up the concept of integrating to find the rotational inertia of an object. Just conceptually, if we take this, we're going to swing a cat around. Please don't do this, but we're going to swing a cat around by the end of the tail. Okay, so the cat's going to go around like this, going to pivot around like that. Just conceptually, we're adding up all the mr squareds, because that's the rotational inertia of a point mass, all the mr squareds in the cat's body. Now, we can go through all the molecules in the cat's body, and we can go do mr squared for every one of them. And I did a bad thing by having these out here. Let's just assume that, well, okay, I'm not even going to worry about that. So I could do that for every single molecule, right? Or what I can do is I can take everything that's the same r squared and group it together as one mass. So r, there's an r right here. We could probably take the way those legs are curved. They're all essentially at the same r from that point of rotation. So I could take the mass of all of that stuff in there, right, and multiply it by r squared, and add it to, I'd have to do it chunk by chunk for every little chunk in here. Okay, so I'm really going from out here, or from in here, from r equals 0 out to the farthest point, which is out here somewhere. And I'm just going to be grouping all the things that are the same r as each other and putting that mass at that total r. So for this band right here, I would take the mass of all of that times that r squared. And if I add all those up, then I get my total I. Okay, and that's kind of like the philosophy behind what we're doing in calculus. Okay, for calculus, once again, if we have this around this point of rotation right here, so if it's irregular objects, even if it's regular objects, we kind of have to use this to get the whole thing, because very frequently we're given rotational inertia for objects. Sometimes we have to actually derive it. So I want to integrate to find the rotational inertia around one end of a rod. We know it's going to end up being ml squared over 3 for a uniform rod. Okay, and this is a uniform mass. What do I mean by that? I mean the density doesn't change. That means a dm right here that's dx wide is going to have the same mass as a dm over here that's dx wide. Next thing we'll do is get a differing density, and then, you know, it's actually not that much worse than this. So, equation for I, when we're doing a differential thing, is dm r squared, sometimes written r squared dm. Right? Well, dm for this thing right here, let's write this as density. And we're going to be talking about linear density. Okay, and the linear density, the mass of the whole rod is m, the length of the whole rod is L. So it's m in kilograms divided by L in meters, kilograms per meter. Okay, that's how much every meter length of this thing has in mass. So that density is lambda. So if we look at a little thing dx wide, m over L, it's also equal to the ratio of dm to dx. I really like to be comfortable enough with density to say that the mass dm is equal to the density, how many kilograms per meter, times how many meters, dx. It's the same thing here if we just multiply dx times this. But if you just want to write it as a ratio, fantastic. It's easier if you can start to think about it like that. So I can substitute for dm lambda dx times, instead of r squared, since we're only operating in x, I'm going to have it as x squared. Lambda, again, is just m over L. M is given, L is given. So m over L dx x squared. M and L are constants, so this ends up being m over L And I'm going to go, by the way, from 0 out to L in the x direction. Okay, I'm integrating over the whole bar lengthwise. Integral of x squared dx from 0 to L. This ends up being m over L times x cubed over 3 evaluated from 0 to L. Since I have the limits there, I don't have to have a plus c in there. This ends up being ml cubed over 3 times L. ml cubed over 3L. And that's the same as ml squared over 3. Pretty happy, because that is exactly what we had learned before, was the moment of inertia around the end of one rod. And what I'm going to do is, on the back of that, I'm going to do it with different density. Okay, so in other words, we've got a rod right there, and we're going to find the moment of inertia around one end, and it has a linear density. Let's call it 5x. Okay, that means it gets more dense as you get closer over there, farther over there. So I'm going to call that my x right there. And so my rotational inertia is going to be the integral of the mass times r squared. We're going to take each little dm, each little mass element that's dx wide. So that dm r squared. And once again, dm, the density is dm over dx. So we can think of dm as equal to lambda dx. And the r squared, we're using x. We're only going in one dimension, so we're going to use that. And I can substitute in my lambda. By the way, I'm going to go from 0 to L. Lambda is going to be 5x. So we have 5x dx times x squared. This ends up being integral from 0 to L of 5x cubed dx. And I've got my integration variable there is consistent with the 0 to L. So this ends up being the integral from 0 to L. 5x cubed dx is 5x to the fourth over 4. 0 to L equals 5L to the fourth over 4. So there's actually doing a varying density. So that's a nice thing to do. Here's some other ones here. A thin hoop, mass m, radius r. Well, guess what? If we're rotating it around that, everything is a distance r away. So this just ends up being mr squared. There's really no integration to be done on this. Very easy, okay? Which is really nice, because then we're going to use this here. We're going to look at a thin uniform disk, and we're going through axis through the center of mass. This is a really important one, because this comes up an awful lot. So if I look down on that, right, what I want to do is, if that's my point of rotation, I want to divide this up into chunks that are all the same distance from the center of rotation. Okay? Those are all the same distance from the center of rotation. So those are a bunch of, we'll call them nested hoops. So I want to integrate all the little di's, okay, the di for each one of these things. And that's going to be the integral of the dm's times r squared, how far from the center. Well, let's figure out what the mass of one of those hoops is. The total mass is m, the radius is r. Well, now we can't do a linear density. We're going to do an area density. Sigma. Sigma is the mass per unit area. In this case, it would be mass per pi r, capital R, squared. That's the density. Okay. And again, the density will also be dm over dA, the area of the little tiny chunk. This is a little harder to visualize, but if this is infinitesimally thin there, we can really think of it as the area as being the circumference, I'll just write circumference, times the thickness. Okay. Yes, if this is very wide, if a disk is very wide, that doesn't end up being true. But if this is infinitesimally thick, it's really like we can cut it there and spread it out into a long line. And so this ends up being dm over 2 pi r dx. And I don't want to run too fast past that because I think this is the first time we see this. If you have like a really thick thing here, if we're talking about that whole business, the area there, if you cut that and opened it up, it would look kind of like this. And that area is not length times height. You got to do something a little crazier with that, right? So if you ever took like a tennis ball, it's impossible to cut it and get it flat. But if you take something that's the width of a human hair, like this, even thinner than I'm showing, where this is very, very, very thin, you cut that, it will lie fairly flat. And so the thickness here, in this case, would be the dr, and the length would be the circumference. So we could just do circumference times dr. And I really wish I'd written dr here, dr up there. So the mass of this is going to be sigma, which is m over a, let me write it as sigma, times 2 pi r dr. Oops, sigma, not lambda. I wrote lambda. Sigma is the area density. Kilograms per meter squared times how many meters squared there are. And then times r squared. Sigma, again, is mass over pi r squared. So we have the integral from 0 all the way out to the end, r, of m over pi r, capital R squared. Very important to keep your r's separate. This r is what we're integrating over. This is the size of the entire disk. So we end up with 2 pi r squared dr, r cubed, sorry, dr, 2 pi little r cubed dr. All of this is a constant. So we have m over, one of the pi's cancel, 2 pi over r squared, integral from 0 to r of r cubed dr. This ends up being 2m over r squared, r to the 4th over 4, evaluated from 0 to r 4th divided by r squared is r squared, m over 2. 1/2 mr squared. That's really, really important. Really important. It is going to be given in many problems, right? Many times they'll give it to you, but you want to be able to derive that. And so it is just picking area density and adding up the rotational inertia of all the things that are the same distance from the center of rotation, adding the m times r squared. It's actually a dm times r squared.